Hi everyone, I'm Pengyu. Today I'm going to present a joint work with Jason, Jesse, and Milos on the naturalness of hardware descriptions. Our work is motivated by the success of many software repositories in the past decade. With more and more developers engaging in open source project development, there are large corpora of software artifacts available in open source repositories, consisting of millions of lines of code, as well as the associated natural language documentations, pull requests, and open issues. By mining this corpora, an important observation that researchers made is that code in programming languages is natural, or in other words, repetitive and predictable, just like text in natural language. Building on this observation, researchers and practitioners built statistical and learning-based models for many software techniques like code completion, code repair, code search, code summarization, and so on. However, existing work and applications have focused almost exclusively on general-purpose languages like Java and C. We are interested in a different set of languages, hardware descriptions languages, which have not yet been explored. Hardware description languages, in short HDLs, are for describing logic circuits. VHDL, Verilog, and System Verilog are the three most popular hardware description languages nowadays. Here I show an example of VHDL code from a GitHub repository. The basic unit in hardware descriptions is module. Each module starts with its interface, describing the input and output ports, and is followed by the behavior. In the beginning of the behavior part, there can be several local signals, which are like local variables in general-purpose languages. Then there can be explicit process and concurrent assignments. Each concurrent assignment is an implicit process. A very unique feature of hardware description languages is that processes, including explicit process and concurrent assignments, are executed in parallel. In this work, we start the research of many hardware descriptions repositories by making the following contributions. First, we mined hardware descriptions repositories corpora from GitHub, totaling 8.5 million lines of code. Then we conducted the first comparative evaluation of the naturalness of hardware descriptions by building language models and reporting standard cross-entropy measures. Specifically, we compared the naturalness of hardware descriptions written in VHDL, Verilog, and System Verilog against the naturalness of software written in Java. Finally, as an application, we designed and implemented deep learning models for predicting the right-hand side of concurrent assignments in VHDL. Let me get into them one by one, starting from the corpora. We mined top 100 repositories from GitHub, ranked by the number of stars for each of the language. We only keep parsable files in our corpus using open source parsers generated using Antler parser framework. We also filter out duplicate files. For each corpus, we compute the lines of code, the total number of tokens, and the vocabulary size, that is the number of unique tokens. To compare the naturalness of hardware descriptions against the code written in general-purpose languages, we also collect two Java corpora. The Java popular corpus here consists of the top 10 repositories from GitHub at the time of our study. We collected 10 rather than 100 to get a similar amount of number of tokens compared to our hardware descriptions corpora. And the Java naturalness corpus here is the 10 repositories from the ICSI 2012 work. These box plots show the statistics of our corpora. There are lines of code per file, number of tokens per file, and number of unique tokens per file respectively. From the length of code per file plot, we can observe that hardware descriptions in VHDL are more verbose than Verilog, as commonly accepted in the community. And also, hardware descriptions in System Verilog is shorter because they are mostly used for verification and validation. Looking at the other two plots, we see that the number of tokens and number of unique tokens are higher in Java repositories than HDL repositories in general. Among the HDLs, the System Verilog one has the smallest number of tokens and number of unique tokens compared to the other ones. Next, I will describe our experiments measuring the naturalness of hardware descriptions. We follow the same methodology used in the ICSI 2012 work. Specifically, we first randomly partition the corpus into 10 equally sized forts. Regarding how to define the corpus, I will describe in detail on the next slide. Then we train a language model on 9 forts and apply it on the remaining fort. Here we use n-gram language model where n ranges from 1 to 10. An n-gram language model computes the probability of seeing the next token given the previous n-1 tokens. We repeat step 2 for all the 10 forts and compute the average cross entropy as a measurement of the naturalness. Prior work on naturalness used 2 different levels to define the corpus. The ICSI 2012 work used the repository level, which means they consider each repository as a mini corpus and compute its naturalness, and then they report the average among all repositories. While the ICSI 2019 work computed it on the language level. Basically, they consider all the repositories of one programming language as a single corpus. The repository level accounts for the variabilities across different repositories in a language, but the language level measures the regularity of each language as a whole. In our work, we measure naturalness on both levels. This line plot shows the results of our naturalness experiments. The x-axis in each plot is the n-gram, n in n-gram language model, and the y-axis is the cross entropy, and each line is for one corpus. Apparently, cross entropy monotonically drops as n increases. Note that in this plot, lower cross entropy means higher naturalness. So this shows that n-gram with higher n can better capture statistical regularity. And the decline of cross entropy saturates at around 4 grams for hardware descriptions. This is similar to the finding in the ICSI 2012 work. We further analyze and compare the cross entropies of different corpora. At the repository level with lower n, the cross entropy for hardware descriptions in all the 3 languages, VHDL, Verilog, and System Verilog, are similar, while they are smaller for code written in Java. With higher n, however, the cross entropy for VHDL is similar to Java Popular and is lower than the other 3, Verilog, System Verilog, and Java Naturalness. At the language level, cross entropy for VHDL is again the lowest, is followed by the System Verilog, Java Popular, and Java Naturalness, which are higher, and the highest is the naturalness of Verilog code. With these observations, we can conclude that hardware descriptions show clear properties of naturalness. And in particular, VHDL code has the highest naturalness among all the 3 hardware description languages, and this is even higher than that of Java software at the repository level. Next, I will describe our assignment completion model. We focus on helping hardware designers to write concurrent assignments. Specifically, our task is given the left-hand side of a concurrent assignment, we are to predict the value on the right-hand side to be assigned. The underlying framework we are using is sequence-to-sequence architecture. As illustrated in the bottom figure, it encodes the sequence into a deep representation and predicts a target sequence as the output. Our input and output sequences are obtained by splitting the code into subtokens separated by spaces and underscores. Based on this sequence-to-sequence architecture, we designed several novel architectures to capture HDL-specific characteristics, including first, multi-source architecture to encode more previous assignments context, and second, to utilize the types of signals, and third, ensembling multiple sequence-to-sequence models to capture the parallel nature of HDLs. The base architecture encodes the left-hand side subtokens using an encoder. However, this ignores the previous context encode, such as the previous assignment. We can observe that the context field from previous assignment, especially its right-hand side, can be very helpful in generating the output. To handle that context, we add an encoder to encode that previous assignments, and combine the deep representation of both encoders using a fully connected layer and a liquid ReLU layer. And we send that to the decoder. I will refer to this model as S2S plus PA1. Similarly, we can add more encoders for more previous assignments. In this work, we experimented with up to 5 previous assignments. I will refer to this model with 6 inputs, left-hand side plus 5 previous assignments as S2S plus PA1 to 5. We also utilize the types of signals in our model. Take this S2S plus PA1 as an example. We perform static analysis to obtain the types of signals. Specifically, we use 13 popular types and plus a t-type representing all the other types. This plot on the right shows their frequency in our corpus. We encode each type as a one-hot embedding, and we concatenate the type embeddings with word embeddings for the signals subtokens. For other subtokens, we concatenate 0 to their word embeddings. I will refer to this model with type as S2S plus PA1 plus type. These models I mentioned so far do not capture the parallel nature of hardware description languages yet. Remind that all the concurrent assignments, including the 5 previous assignments here, are executed in parallel. That means their order should not matter in the model we designed. However, suppose we use S2S PA1 to 5 plus type to handle all the inputs together. That is not the case because each previous assignment is handled using a different encoder and they are processed one after another. Instead of that, we use 5 multi-source sequence-to-sequence models. Each takes 2 inputs and each of them handles one of the 5 previous assignments. Each of them generates an output such as O1 with a confidence score such as C1. To ensemble these models in a way that their order do not matter, we use a regression model. The inputs to the regression model are the confidence scores and the features extracted from the multi-source model's outputs and inputs. The regression model is to choose one out of the 5 outputs given the input features as a prediction. Additionally, we observe that the right-hand side of the 5 previous assignments can sometimes close to the target output. For example, here, the right-hand side of the first previous assignment is very close to the expected output. That means it can be good backup options if none of the O1 to O5 are good. We enable our regression model to choose them as well. So our final regression model is to choose one out of the 10 options. I will refer to this model as S2S plus PA enzyme 1 to 5 plus type. To train and evaluate our models, we collected a dataset by extracting all concurrent assignments from our VHDL corpus. We split the dataset into training, development and testing set with a ratio of 80%, 10%, and 10% respectively. The development set is used for tuning the hyperparameters of our models. We follow the following steps to ensure that the assignments from the same file are not partitioned into multiple sets. Specifically, we first random shuffle all the files, and then we take enough files to obtain around 10% assignments for the testing set, and then another 10% for the development set, and the remaining goes to the training set. We compare the following baselines and models in our evaluation. For rule-based, the rule-based baseline always copies the right-hand side of the first previous assignment. For the language model baseline, which resembles the code completion techniques, we select the best language model, RNN language model, using the left-hand side plus first previous assignment as context, out of all the other options we tried. In our experiments, we observed that language models are not good at handling long contexts. For example, the RNN language model with only the first previous assignment as context is even better than the RNN language model with all 5 previous assignments as context. These are the sequence-to-sequence models that I will compare in this talk. We use automated metrics in our evaluation by computing the similarity between the predicted right-hand side versus the human written right-hand side for each data in the testing set and report the average scores. We use the 3 similarity measurements: exact match rate, subtoken level accuracy, and BLEU, which computes the percentage of n-grams matches. This table compares the performance of the rule-based baseline, the language model baseline, and our best model. The best model is a sequence-to-sequence model that resembles multiple multi-source models for 5 previous assignments with utilizing types of signals. It achieves 37.3 BLEU score, significantly outperforming the baselines. This table compares the different sequence-to-sequence models. We can observe that using more previous assignment context and type embedding improves the performance over the best architecture. And comparing the first 2 lines, we find that ensembling handles the previous assignment context more effectively than only using multi-source architecture, because it captures the parallel nature of hardware description languages. That concludes my talk. More information can be found in our paper. Our data and code are available in our GitHub repository. Thank you for watching.